Good morning, students. Next topic is factors determining the magnitude of crystal field splitting. In this, we will discuss the factors which affect the crystal field splitting. And first factor is the nature of ligand. Second is the oxidation state of metal ion. Third is the type of d orbitals, and fourth is the geometry of the complex. Now we will discuss first factor, that is the nature of ligand. Crystal field theory that depends upon the nature of the ligand. The greater the ease with which ligands can approach the metal ion. If ligands that is more approach to the central metal ion, it means ligands electron that will interact with the metal d orbitals, then there will be more repulsion and there will be greater crystal field splitting. So crystal field splitting that depends upon the nature of ligands. There are two types of ligands. One will be strong field ligands, other will be weak field ligands. The ligands which causes large splitting that are called strong field ligands, and the ligands which causes a small degree of crystal field splitting that are called weak field ligands. And this splitting is caused by a number of factors, such as if ligand size is small, then that will cause greater crystal field splitting. They will approach the central metal ion very closely. For example, F negative ion produces greater crystal field splitting as compared to Cl negative ion, because Cl negative ion, Br negative ion, that is having larger size than the F negative ion. Second, the ligands which are easily polarizable electron pair, so in which there are easily polarizable electron pairs, that will causes greater crystal field splitting because they will be drawn more closely to the central metal ion. Third point is ligands which have greater tendency to form multiple bonds, such as Cn negative, NO2 negative, that will causes greater crystal field splitting. So Cn negative, that is a strongest ligand that will causes more crystal field splitting as compared to halide ions that are weak field ligands. So this is the order of increasing sigma donation, that is the firstly carbon donors, then nitrogen donors, then oxygen donors, then halide donors. So carbon donors that will causes greater crystal field splitting than nitrogen donors, then oxygen, then halide donors. So in these, metal ion donates electrons from the filled T2g orbital into the vacant orbital of ligands. So there will be metal to ligand electron pairs transfer, and this is for more crystal field splitting. So for the ligands differentiation, we are having spectrochemical series. Spectrochemical series is a arrangement in an increasing order of crystal field splitting. So this is the arrangement of ligands in the order of increasing crystal field splitting. For example, I negative, Br negative, SCN negative, Cl negative, all these are weak field ligand, whereas CO, Cn negative, NO2 negative, orthophenanthrolene, so all these are strong field ligands. So this is the order of ligands strength, that is the spectrochemical series. So greater the strength of ligands, strong field ligands, that will causes greater crystal field splitting. So next is the oxidation state of the metal ion. So crystal field splitting also depends upon the oxidation state of the metal ion. So the metal ion with the higher oxidation state, that will having more approach to the ligands, and there will be more repulsion, and this will cause larger crystal field splitting than the ions with lower oxidation state. For example, the complex cobalt water 6 3 positive and cobalt water 6 2 positive. In this cobalt 3 positive and cobalt 2 positive, naturally the cobalt 3 positive is having greater oxidation state as compared to cobalt plus 2. So there will be more crystal field splitting of cobalt water complex 3 positive. It means that is having 18600 centimeter inverse, whereas cobalt 2 plus is having 19 300 per centimeter. So greater the oxidation state of central metal ion, greater will be the crystal field splitting. Similarly, water H2O6 3 positive and water H2O6 2 positive, that is also plus 3 oxidation state, that is higher oxidation state. So there will be greater crystal field splitting. So this is the oxidation state of central metal ion. Next is type of d orbitals. The extent of crystal field splitting also depends upon the type of d orbitals. As we move from 3D to 4D series, then crystal field splitting increases 30 to 50%, and also if we move from 4D to 5D, this also increases 30 to 50%. So as 3D to 4D and 4D to 5D, the crystal field splitting increases because 4D orbitals are having greater size as compared to 3D orbitals, and they will be more occupy in space, and they will be extended larger into space, and this will be more approach to the ligands, and there will be more interaction, and there will be ligand orbitals, ligand electrons, and d orbitals having electrons. There will be repulsion, and this will cause greater repulsion and greater crystal field splitting. Similarly, 5D orbitals are also bigger than the 4D orbitals, and there will be greater crystal field splitting. For example, cobalt, rhodium and iridium with ammonia complex, cobalt plus 3, rhodium plus 3 and iridium plus 3. So cobalt is a 3D group, rhodium is a 4D series group, and iridium is a 5D series group. So 3D6, 4D6 and 5D6. So crystal field splitting increases from cobalt to iridium complex. So next point is the geometry of the complex. In this we will discuss octahedral and tetrahedral. Crystal field splitting in case of octahedral complexes is greater than the tetrahedral complexes, and delta T is equal to 4 by 9 delta O, that is we have discussed earlier. So because tetrahedral, there will be crystal field splitting is less than the pairing energy, and they will always form high spin complexes. Why crystal field splitting in octahedral is greater than tetrahedral? Because there are 6 ligands in octahedral, whereas tetrahedral having only 4 ligands. So greater the number of ligands, greater will be the crystal field splitting. Second point, and in case of tetrahedral case, none of the ligands are exactly towards the approach of the ligands. So none of the ligands are exactly towards the axis of the d orbitals. So there will be no direct repulsion, and there will be less crystal field splitting. So all these are the 4 factors which affect the magnitude of crystal field splitting. So all these are topics in metal ligand bonding in transition metal complexes. Thank you, students.